Good afternoon, everyone, and welcome to today's Safer Sim webinar. Today, we are going to learn about a research project that was completed by the University of Central Florida, and they took a look at road safety risk mitigation under reduced visibility and using a driving simulator. So I will let our presenter, Yina Wu, take over from here. And
Thank you,
please use
Jacob.
the chat box for any questions. Thanks, Yina.
Okay. Thank you, Jacob. Hello, everyone. Thank you for attending this webinar. The title of this webinar is A Driving Simulator Investigation of Road Safety Risk Mitigation Under Reduced Visibility. My name is Yina from University of Central Florida. My advisor is Dr. Ati. Next slide, please. The presentation today will include 4 parts. Firstly, I will briefly introduce the research background. Then, we will discuss about the experimental design of the driving simulator experiment. Finally, after that, we will discuss about the experiment results. Finally, I will explain the summary and conclusion. So firstly, let's look at the introduction. Next slide, please. Fog is an adverse weather condition with reduced visibility and has a significant impact on driver behavior, traffic flow characteristic, and traffic safety. Compared to crashes happen under clear condition, fog-related crashes are prone to be more severe and involve multiple vehicles. According to fatal crash statistics from National Highway Transportation Safety Administration, fog contributed as a major factor to more than 7,000 fatal crashes that have occurred in the United States from year 2000 to year 2015. In year 2008, a 70-vehicle involved pile-up happened in Florida, causing 5 fatalities and many injuries. Another example happened in year 2012. At least 10 people were killed in that crash. Next slide, please. So in previous studies, a number of studies have investigated the change of driver behavior under fog condition. Since some drivers tend to reduce their headway distance during fog, they may not be able to have enough response time to react to dangerous situations, even if they had reduced their speeds, which results in an increase of rear end crash risk. Our previous study analyzed the traffic pattern and found that both volume and speed under fog condition dropped significantly. By proposing a crash risk increase indicator, we confirmed that crash risk could increase under fog condition. We also have investigated the impact of fog warning system, which include variable message signs and beacons, as it is shown in the pictures, on driver's speed adjustment for fog condition using a driving simulator study. We found that the warning system could significantly affect drivers' speed adjustment before they drive into the fog area, but could not sufficiently change drivers' final speed after entering into the fog area. Next slide, please. In recent years, connected vehicle crash warning systems are gaining increasing attention, which display a vista for enhancing traffic safety under fog conditions. Previously, crash warning systems were based on sensors and video cameras. However, bad weather could reduce the system's accuracy. Connected vehicle could further improve the performance of crash warning system by deploying vehicle-to-vehicle communication or vehicle-to-infrastructure communication. The vehicle-to-vehicle communication can provide real-time position and speed of the lead vehicle. Thus, the crash warning system can detect the sudden slowdown or stop of the lead vehicle and timely alert the drivers of the following vehicle with an in-vehicle warning messages. Many driving simulator studies have conducted to explore the impact of crash warning systems, while drivers' response time, throttle release behavior, brake pedal behaviors, and time to collision could be deployed to evaluate the effectiveness of crash warning systems. Next slide, please. The safety benefit of crash warning system have been evaluated in previous literature, and many studies have indicated that the warning system could effectively help reduce rear-end crashes. However, there is lack of study on the safety effectiveness of crash warning system on rear-end crashes under fog condition. Therefore, different from our previous study, which investigated the effect of warning system on drivers' behavior in fog, the current study aimed to examine the effect of crash warning system on drivers' rear-end crash avoidance behavior under fog condition, based on a driving simulator experiment. Specifically, the objective of this study is to investigate whether warning systems have significant effects on drivers' rear-end crash avoidance performance when the lead vehicle makes an emergency stop. So now, let's look at the experimental design of this study. The experiment was designed as a mixed factorial design with warning type as the within subject variable, fog level and age as between subject variable. Our previous study suggests that fog could have significant effect on drivers' behavior when the visibility distance is less than 300 feet. So the visibility distance of 300 feet was selected as the moderate fog condition in this study. Also, it was suggested that driver could have very high crash risk in fog condition when the visibility distance is very low, since driver could not have enough time to respond to an emergency. So 100 feet visibility distance was selected as dense fog condition to test the effects of warning system under dangerous situation. Meanwhile, it was found that drivers' behavior might be vary at different age group, so driver's age is also considered in this study. As it is shown in the table, the participants were divided into two groups, which are the B1 group and B2 group. And each participant would run through the 3 scenarios in each group during the experiment. Next slide, please. The next advanced driving simulator was used for this experiment. The simulator provides a 130-degree horizontal by a 24-degree vertical field of view in front of the seated participant with 3 screens. 2 speakers was installed in front to simulate the sound of passenger cars, as well as deliver the audio warning messages. And the 3rd speaker was mounted below the driver's seat to simulate road vibrations. Next slide, please. As we can see from the picture, the test warning messages were presented through the HUD interface at the bottom of the middle screen, which was set to be transparent and would not obstruct the participant's view. The simulator was equipped with a 4-channel video capture system and collected driving data at a rate of 60 Hz. Totally, 54 participants were recruited in this study, regardless of the driver's other socioeconomic status. Each fog level has 27 participants, with 9 participants in each age group, and each participant performed the experiment under 3 warning conditions, which include no warning condition, HUD warning only condition, and HUD with audio warning conditions. So these figures show the moderate fog condition and the dense fog condition during the experiment. During the experiment, the participants start to drive on the outer lane of a 4-lane straight roadway segment under clear condition. A lead vehicle was placed in front of the test vehicle with a speed of 50 miles per hour. The driver was asked to drive from the clear condition to fog condition and not overtake the lead vehicle. 54 participants were recruited for this study. The average age of the participants was about 38 years old, ranging from 18 to 75 years old. Each participant should have a valid driver license, and and had at least 1 year of driving experience. The experiment lasted for about 30 minutes in total for each participant. IRB approval was obtained before starting the experiments. Upon arrival at the lab, each participant was briefly introduced to the requirement of the experiment, and all participants were required to read and sign a consent form. Participants were notified that they could quit the experiment at any time in case of motion sickness. Before formal experiments, the participant had at least 10 minutes to get trained and be familiar with the operation of the driving simulator. Then they performed a formal driving simulator experiment under either moderate or dense fog condition with 3 different warning conditions in a random order. It should be noted that the gender of the participant was also carefully considered when assigning the age groups. Between each trial, participants could have at least 5 minutes to have a rest. After the experiment, the participants were required to finish a survey about their experience with the scenarios. Next slide, please. Yeah. During the experiment, after the lead vehicle started to decelerate, the warning message would be delivered based on the headway distance between the start vehicle and the lead vehicle. To avoid the cry wolf effects of premature warning message, the headway distance for delivering warning message was carefully determined. So now let's look at a short video which shows an example of the studied scenario. Yep. Yeah, as we can see from the video, during the experiment, once the warning system was triggered, the HUD warning would display the words of slow vehicle ahead for about 1 second. The HUD and audio warning delivered a beep sound along with the HUD messages. Next slide, please. When the participant received the warning message, the lead vehicle could have 3 different status: start to decelerate, decelerating, and stop. For the 3 different status, the minimum stop distance for the test vehicle would range from 110 feet and 351 feet. Hence, in this study, the warning message was delivered when the headway distance between 2 vehicles was less than 400 feet. Also, such design could ensure that the participant would receive the warning message before they saw the brake light of the lead vehicle. We have some short videos to demonstrate the driver crash avoidance behavior during the experiment. So the left, one video will show the change of the lead vehicle and the follow vehicle's speed, and another video will show the status of the throttle pedal and the brake pedal. So from the video, we can find that driver will release the throttle when they notice the event and then begin to use the brake pedal. Next slide. Yeah. Okay. So this figure shows a typical example when the lead vehicle was braking. Based on the key time moment shown in the figure, several critical measurements was defined to evaluate the participant driving performance: time to initial throttle release, time to final throttle release, time to initial brake were used to analyze driver's throttle release behavior. Time to initial throttle release is defined as the time between the onset of the lead vehicle's braking and the moment when the participant begins to release the throttle pedal. Time to final throttle release is defined as the time between the moment when the participant began to release the throttle pedal and the moment at which participant completely released the throttle pedal. Time to initial brake is defined as the time when the participant completely released the throttle pedal and the moment at which participant begins to press the brake pedal. Similarly, time to 25% of brake, time to 50% of brake, time to 75% of brake, time to maximum brake were also used to analyze the status of brake pedal. Three other dependent variables are included in this study. The first variable is the brake reaction time. It is defined as the time between the lead vehicle brake onset and the time when the participant begins to brake. The second variable is the minimum time to collision, which is defined as the time it would take for the test vehicle to hit the lead vehicle, given that their current speeds are maintained. The minimum value is selected from the time interval between the moment when the lead vehicle starts to brake and the time the driver brakes to stop behind the lead vehicle. The last variable is the maximum brake pedal pressure, which is the maximum value of brake pedal pressure observed during the braking event. For the measurements of the participants' rear end crash avoidance behavior, the repeat measure maneuver was conducted for throttle release measurements and brake transition time measurement, in which high correlations were expected. Maneuver is a type of multivariate analysis that can be utilized to conduct data analysis for the data with more than one dependent variables. Maneuver control the overinflation of type 1 error. Repeat measure ANOVA was then conducted on the significant variable found by maneuver analysis. For the significant factors with more than two groups, a set of post-hoc analysis was conducted to further compare the differences. For the other measurements, including response time, minimum time to collision, and maximum brake pedal pressure, only repeat measure ANOVA and post-hoc analysis was performed. The statistical significant level was said to be 0.1 level. So now let's move on to experiment results. Although 54 participants were recruited in this experiment, only the data of 48 participants were collected for the analysis, since 6 participants could not finish the experiment due to motion sickness. In the complete 144 trials, 7 trials was excluded because some participants chose to steering wheel instead of braking to avoid hitting the lead vehicle, and some participants drive too slow and were not able to follow the front vehicle. So a dataset containing information for 137 trials was created for this analysis. For the result of the questionnaire, more than 90% of the participants thought the driving simulator had a high level of realism and the HUD was helpful, while only 60% of the participants thought the audio warning sound was helpful. Three measurements was employed to assess the participant throttle release time, including time to initial throttle release, time to final throttle release, and time to initial brake. The repeat measure maneuver analysis suggests that only warning type has significant effect on driver throttle release time. However, no significant effect of fork level, age groups, and gender could be observed in terms of throttle release time. The ANOVA results indicate that the time to initial throttle release and time to final throttle release contribute to the multivariate effect. As it is shown in the table, the result of post-hoc tests suggests that participants under no warning condition need more time to start and finish the throttle release behavior. Since driver could know the hazard event earlier by the warning system, they could take earlier reaction to avoid the potential collisions. However, there was no significant difference between HUD-only warning and HUD with audio warning, which indicated that adding audio warning system could not significantly affect participant awareness of upcoming accidents and hence could not shorten the throttle release time. The second variable is the brake time. Participant brake transition time was examined by 4 measurements, which are the time to 25% of brake, time to 50% of brake, time to 75% of brake, and time to maximum brake. The MANOVA test shows significant effect of warning type and age. However, there was no significant difference between moderate and dense fog condition in terms of brake transition time. The subsequent repeat measure ANOVA analysis showed that warning type has significant main effect on both time to 75% of brake and time to maximum brake. As is shown in the table, the post-hoc test indicate that time to 75% of brake and time to maximum brake become longer under no warning condition compared with the HUD with audio warning condition. No significant difference could be observed between the two different warning types. In addition, the ANOVA test result of age shows significant impact on time to 75% of brake and time to maximum brake. The post-hoc test suggests that young drivers tend to spend longer time to reach to 75% of brake and maximum brake pedal position compared with working age and old drivers. However, no significant difference was found between work age and old drivers. The third variable is reaction time. The influence of warning type, fog level, gender, and age on brake reaction time was examined through similar repeat measure ANOVA test. The effect of warning and age was significant. However, fog level and gender did not have significant impact on brake reaction time. This figure presents the mean brake reaction time for different warning types and different age groups. From the result of post-hoc analysis, there was significant difference of brake reaction time between no warning condition and the HUD with audio warning condition. Compared with no warning condition, HUD with audio warning condition has less brake reaction time. It was also useful to note that no significant difference could be observed between the HUD-only condition and the other two conditions. Regarding the effect of age, the brake reaction time was the largest in old age group, which indicate that old drivers need more time to respond to emergency events. However, the differences between young driver and work age driver was not significant. The minimum time to collision is an essential surrogate safety measure to evaluate rear-end crash risk under fog condition. The ANOVA analysis suggests that the effect of warning type and fog level on minimum time to collision are significant, while the effect of gender and age are not significant. The mean minimum time to collision of different warning type and different age fog levels are present in the figures. The post-hoc analysis indicate that the minimum time to collision under no warning condition was significantly lower than that under HUD-only condition. Although the HUD-only condition has higher minimum time to collision compared with HUD with audio warning condition, the differences was not significant, which may due to the random effect. With the warning system, driver could become better prepared to avoid the potential conflict. The right figure suggests that smaller minimum time to collision could be found under dense fog condition. Compared with moderate fog condition, the finding indicates that rear-end crash risk could increase when visibility distance decreases, which is consistent with previous studies. The last variable is the maximum brake pedal pressure. The ANOVA analysis shows significant effects of fog level and age on maximum brake pedal pressure. However, warning type and gender did not significantly affect maximum brake pedal pressure. The result of warning type indicate that the warning message would not affect driver's maximum brake pedal pressure if the participant have realized the risky situation through either seeing the brake light of the lead vehicle or noticing by the warning message. The mean maximum brake pedal pressure for different fog level and different age groups are shown in the figures. The left figure indicates that driver would employ a larger brake pedal pressure under dense fog condition compared with moderate fog condition. As for the effects of age, old drivers tend to have larger maximum brake pedal pressure compared with the other two age groups. And there is no significant difference of the brake pedal pressure between young driver and working age drivers. So finally, let's discuss about the summary and conclusion. Previous studies suggest that drivers could have better decisions if they get prepared for the upcoming road conditions. Whether driver could successfully avoid the rear-end crashes depends on how quick the driver can identify the upcoming crashes and conduct crash avoidance actions. In this study, both shorter throttle release time and shorter reaction time could be found with the presence of warning system, which indicates the advantage of warning system. Meanwhile, driver's brake process could be smoother with the warning systems. In addition, driver could have greater minimum time to collisions with warning system, which confirm the benefits of crash warning system under fog condition. In this study, both the start moment of warning message and the moment when participants see the brake light of the lead vehicle could be regarded as stimulus, and the response to the stimulus of each driver under emergency situation is relatively similar. So driver would have similar maximum brake pedal pressure. Meanwhile, previous studies suggest that multimodal crash warning systems could further improve drivers' rear-end crash avoidance performance. However, no significant difference was identified in participant throttle release time, brake transition time, or other performance measurements between HUD-only group and HUD with audio warning groups in this study. This phenomenon is possibly due to the fact that drivers are prone to be more careful when they driving under fog conditions. Car following in fog is a complex task since participants need to consider the interaction between their speeds and the lead vehicle's speed. Previous studies have confirmed that participants tend to adopt safer driving behaviors under fog conditions, such as reducing speed and getting less distracted to avoid potential crash arising from the reduced visibility. In this study, no significant effect of fog level was observed for the participants' throttle release time, brake transition time, and response time, while participants would press the brake pedal harder in dense fog condition. However, relative smaller minimum time to collision was found under dense fog condition, which indicate that the increase of brake pedal pressure was still not sufficient to compensate the increase of risk caused by reduced visibility distance. When fog became dense, participants in the test vehicle could not see the brake light of the lead vehicle, resulting in high rear-end crash risk. As for the effect of age, old participants had significant longer brake reaction time because they need more time to do mental calculations. Although working age driver need longer brake reaction time compared with young drivers, although the differences is not significant. In addition, young participants spend longer time to reach to 75% of brake and maximum brake pedal pressure, which means that their braking process could be smoother than other participants. Meanwhile, since old drivers start to brake relatively late and they were more sensitive to the potential risk, they had to make harder brake to avoid the crashes. Although some of the previous studies found that male drivers are more likely to engage in risky driving behavior, no significant gender effect was found in this study, a result in line with other previous fog-related driving behavior study. It might be because that when driving in fog, male drivers' risky driving behavior might be counteracted by the speed and other compensation behavior in fog. So this study investigated the effectiveness of connected vehicle crash warning system on participants' performance during the process of rear-end crash avoidance under fog conditions. Scenarios were specifically designed for rear-end crashes caused by the emergency stop of the lead vehicle. These experiments were designed to test different warning types along with different fog levels and participants' age group. This table summarizes the effect of the tested factors on participants' rear-end crash avoidance behavior. Participant throttle release time is only affected by the warning type, while participants' brake transition time could be affected by both warning type and age. Response time could be affected by warning type and participant's age. In addition, minimum time to collision is affected by warning type and fog level, while maximum brake pedal pressure could be affected by fog level and age. Next slide. Yeah. To conclude, the experiment results indicated the positive effects of crash warning system on safety. It was found that the warning system can significantly reduce drivers' brake response time and increase minimum time to collision. Also, no significant additional effect of audio warning could be found. The decrease of visibility distance could increase the crash risk, and all drivers are more vulnerable road users under fog condition. No significant gender effect could be identified in this study. Thank you. I will be happy to take your questions.
Thanks, Yina. So if there are any questions, feel free to type them in the chat box. Okay, I'm not seeing any questions at the moment. I do want to, as I always do, I'll get a good pitch in for the next webinar that'll be on Tuesday, April 24th. So that'll be at the normal time at 2 p.m. Central. So look for an announcement next week about that webinar. This webinar from Yina today will be on our SaferSim website and the YouTube page by the end of the week. So we'll be sure to circle that link around when it's ready. So once you get that, feel free to share that to anyone that may be interested. And I think if you do have any other questions that you want to follow up with Yina, you can find her on the UCF website. Um, and I think that is all we have for today. So thank you for the presentation, Yina, and thank you all attendees for coming today. We'll see you at the next one.
Thank you.